In the previous video in this series, we set up a multi-phase mixing model and defined the phase interactions for this problem. In this video, we'll set up and run the multi-phase reference frame simulation using cell zones and interpret the solution data. The key to setting up an MRF simulation lies in the specification of cell zones. This is where the motion of each component within each reference frame is defined. Below, you'll notice that 3 cell zones are listed. This cell zone contains the Rushton blade impeller, which is set to rotate at 450 RPM in the absolute reference frame about the z-axis. Likewise, the second cell zone contains the pitched blade impeller, which is also set to rotate at 450 RPM in the absolute reference frame about the same axis. The final cell zone comprises the rest of the tank, which is stationary in the absolute reference frame. Any boundary condition located within a particular cell zone uses the same reference frame as the cell zone. This is why the wall boundary condition for each impeller is stationary. When the multi-phase model is specified, options controlling the initial velocity and volume fraction of each phase entering the inlet become available. Since I'm using the dispersed turbulence model, I only need to set turbulence specifications for water. In this case, exclusively air will be entering the inlet, which is reflected by my volume fraction setting. The calculation is now ready for submission to the solver. The solver will use the coupled scheme and the run is pseudo-transient. I'll use an automatic time step method with a timescale factor of 1. The solution should converge after 850 iterations. After 850 iterations, the convergence of the solution is satisfactory. Let's take a look at the produced flow field. Shown is a contour map describing the volume fraction of air on the XZ plane. This plot shows how the air travels up the mixing tank as it interacts with each impeller. When I change the viewer to look at the XY plane, I can see that the air is collecting on the bottom surface of the Rushton blade turbine disc before it's dispersed by the impeller's blades. The shape of the Rushton blade turbine seems to be creating cavities behind the turbine. Here I've plotted a velocity vector map showing the movement of the water phase throughout the reactor. I can clearly see how the water circulates throughout the tank. Notice that the water forms a closed loop since it cannot escape the tank. Now I can calculate the torque about the shaft for the Rushton blade turbine. In this case, the impeller is rotating counterclockwise about the shaft which lies on the z-axis, so I'll set the moment axis to -z and compute the torque. That seems like a reasonable value. Using this data, I can compute the Rushton blade impeller's power number and compare that value to the empirical model. This concludes this demonstration showing you how to solve a multi-phase mixing problem using Ansys Fluent.